Now I lost everything.
So if you'd like to get dinner with Annika,
Can you see it now online or not? Not at all.
Can you change the slide?
Yeah, let's do this again.
It did just crack.
Yeah, saw that.
And then if you're not going to dinner, there is a party on tap tonight. 6:30 at the mansion.
we can encourage our speaker maybe show up there as well. We cannot take her schedule anymore. Why not? Another. And so I will just end my very, very quick introduction here, and we'll resume the talk as soon as it works.
It's still the presenter.
Can't get out of it for some reason. I don't really want to be in that presenter view.
I find, can you get back to your Zoom window? And then
Yeah.
If you don't stop presenting, I find it's weird.
Okay, okay, let's see. Here we are. For some reason, the Zoom meeting.
Yeah. It's going to be we have a fun. I think.
Okay, I'm just gonna share.
Yeah, we do desktop too.
Okay.
You start presenting, I think. Wow.
Okay, do this again. All good? Okay, great. Okay.
No. No, I usually make a no.
Okay. Okay, well, thanks. After some delay, we're gonna get started. And thanks very much for the introduction and for the invitation to be here at TRIUMF University to present at the MI seminar. So I was gonna come here to talk about something completely different, as Mahi was saying, but today we're gonna go and explore some topics in nuclear astrophysics and understanding the inner workings of stars. And you're going to see a bit of a viewpoint from the experimental side from me. Always good to start with something profound. I'm sure I don't want to bore you with the quote, but always good to remind yourself of where we are or how we fit into this universe. And I'm sure you're familiar with the famous slogan that we're all made out of star stuff. So naturally, you're kind of asking yourself the question, oh, can you even see the title there? So naturally you're kind of asking yourself the question then, okay, these elements that we're all composed of, what is their origin? So astrophysics is really like a field of multiple fields. So you have the astrophysics part, you have the nuclear physics part, computational science, and observational astronomy. All of these astronomical events like supernovae, X-ray bursts, all of these explosive events, they leave imprints in our observable universe in form of the chemical elements. And you can actually detect their signatures by means of satellite missions or by analysis of pre-solar grains found in meteorites, for instance, to learn about the elemental abundance contributions of the various natural elements. And we know that essentially nuclear physics is determining the life cycle of a star from beginning to the very end. And what we want to understand is really like the nature of the type of reactions that govern the energy release, as well as the nuclear physics pathways in these stellar environments. Okay. I lost my cursor. There we go. Okay, so can't do a nuclear astrophysics talk without showing the famous nuclear chart. So, of course, there's our way to classify the isotopes in terms of their proton-neutron number. We all know that the stable ones are in the diagonal, the black ones, and we're trying to understand the various processes in stars along the nuclear chart that are responsible for the creation of these various isotopes. So we have the stellar fusion, which happens in main sequence stars, for instance, all the way up to iron, more massive stars. Then we have the famous S process, which is kind of along the line of stability here, where you have a series of slow neutron capture processes followed by beta decay. So it's a process that happens over thousands of years, for example, in HV stars or massive stars, responsible for about half of the creation of half of the elements beyond iron germanium region. Then the famous R process on the neutron-rich side, where you have very fast neutron capture series followed by beta decays. Here, The origin is still a little bit under debate. We're going to talk about that a little more in a bit. But of course, neutron star mergers, black hole mergers are the most obvious sites. But there's also other options like core collapse supernova, for instance. Now, then we have other processes like the P process, which is responsible for more proton-rich nuclei, where we have 35 of them on the stable side that we can't really tell exactly how their abundance has been created, because it's kind of shielded from the F and the R process. So there's a different type of process that is responsible. And then the RP process, again, like the R process, but with protons, like rapid proton capture processes and X-reverse or classical novae, so binary systems. And then the neutrino P process might be happening in core collapse supernovae stellar winds. And it might be a way to explain, again, some of the abundance distributions in the P nuclei, which can't be explained by the P process by itself. So this is kind of the big overview of all the different types of reaction cycles that and processes that might be happening. So we kind of have to start to break that down. And where do we start as an experimentalist to understand these reactions? So there's a lot of these processes have underlying proton or alpha-induced reactions, which are so-called radiative capture reactions. And that is essentially just the fusion of a nucleus with one or more nuclei and by the emission of a gamma ray. So these are hugely important in nuclear astrophysics. They can occur directly into a bound state or via particle unbound states. It can also happen, and it means it can also happen in resonance. So there's two competing mechanisms, which are illustrated here. So first, you essentially have your initial system capture on your initial nucleus, and then you can have the capture process happening in a direct way. So you basically go into a bound state directly, or you can go into an unbound state first, which then decays, or you can have the resonant scenario, where you're essentially populating excited states. You're forming a compound nucleus, which is an excited state, which then decays down and back into the ground state. And of course, if you're at this kind of resonant level, then you're looking at a huge enhancement in your cross-section, which is essentially shown here. So here you have direct capture, which has less energy dependence, and whenever you have resonance involved, then your cross-section will spike up significantly. So that's why these resonance states are usually the determining areas for your reaction cross-section. So why are they so influential in nuclear astrophysics? Well, they power our stars, starting in the PP chain CNO cycles, in the explosive scenarios, all the way up to supernovae. And they're usually the only proton or alpha-induced reactions that have a positive Q value. That means we really need to know these reaction pathways. They also proceed rather slowly. So in some reaction cycles, they're the limiting step in these nucleosynthesis pathways. And the problem is, however, that they're vanishingly small. So they're very difficult to measure. So what you see here on the left is, again, just a zoom in of the nuclear chart. And just want to show you in red circled here are experiments using radioactive nuclei and performing radiative capture measurements on those. So it's really a limited number of measurements with radioactive species that you can make these measurements with. Whereas for stable ones, of course, a lot of these have been targeted already. But yeah, so for many of the short-lived isotopes, we still lacking measurements. Okay, and how do we do that? Well, kind of giving it away here, but giving it away here, you need rare isotope producing facilities, you need intense beams, low background environments for these really small cross sections, and of course, feasible targets. So let's break that down and start with the beam production pathway mechanisms. So first of all, we're doing these experiments at TRIUMF, and we're performing them in inverse kinematics. That means we're kind of getting around the problem of a radioactive target. So what you see here is essentially the kinematics depicted. So you have your beam particle with mass m1, it's incident on your target with some mass m2. And then, of course, they form the excited compound nucleus with your laboratory energy T3, which is essentially just your beam energy minus the center of mass energy of beam and target. And then we know that the subsequent emission of a gamma ray can only remove energy from that system. And that means that your production, you produced recoil will only have a lower energy than your incoming beam. So it's something you need to consider if you think about how you want to perform these measurements eventually. Now, the advantages of inverse kinematics is that you can use what we do, in our case, gas targets, can purify them quite nicely. You can detect the gamma rays as one of the signatures for the reaction having the reaction happen, and you can also detect your product. So that's the idea behind it. So in terms of beam production, we do that at TRIUMF. And I'm not sure how many people here are familiar with TRIUMF already, or just a handful, not even. Yeah, okay. Almost everyone. Okay, so anyway, TRIUMF is Canada's Particle Accelerator Center. And at the heart of it is our cyclotron, which is a sector-focused cyclotron, which produces a proton beam, which is our driver beam for our isotope production. So essentially, we're accelerating hydrogen ions to 3/4 of the speed of light, and then extract them through thin carbon foils, which strips off the electrons, and then you're left with a bare proton beam, which you can then send to the ISAC target stations. And I should quickly acknowledge that TRIUMF is actually situated on the traditional territory of the Musqueam people, so always has been a seat of learning and something we just want to remind ourselves of. Okay, so after producing the proton beam, we send them to the target stations where we use the so-called ISOL method to produce beams. And I got this slide, I borrowed it from a colleague who had this in one of his previous talks. And of course, that's not TRIUMF directly, but it's made by the Isolde group. So what you have is here your stack target disk stacks, where you have your driver beam impinging. Then you have all kinds of processes like spallation, fission, fragmentation that breaks up your various particles. Then they diffuse, the target is heated. Then they diffuse into the ionization region, into the ionizer tube, and then eventually you can extract them with some type of ion source. Send them along. Of course, now you still have this cocktail of beams, and you want to separate that. And you can do that via mass separation, and a regular mass separator, which we do that at TRIUMF. And then you send them to the various types of experiments that requested a specific species. So, bird's eye view, how the whole thing happens. You have a cyclotron here, and then you send the proton beam to the two target stations where what I just showed happens, essentially. And then you extract the beams and send them to the ISAC experimental areas. For what we're interested in today, again, a beam comes in, hits the targets, gets mass separated, and then we send it upstairs into the experimental halls. It can go into the low energy regions where we have facilities like Titan, for example, for mass measurements, or it can go further into the medium energy region where we have the nuclear astrophysics experiments like DRAGON that we'll be mainly talking about today. We can go through superconducting linear to even higher energies where we have experiments like the EMMA mass spectrometer or the Tigris gamma detector array. Okay, so let's focus on DRAGON. So the DRAGON recoil separator has been around for a few years. And before we're going to say how we're measuring things, just a quick reminder of what our observable is. So what we're after in these experiments is the thick target yield, which is essentially just your number of recoil detected over number of beam particles impinging on your target times your detection efficiencies. And then your total yield depends also on the cross-section integrated on the entire target length. So that also plays an important role. You have your number density, and the reaction yield is depending on that. So the resonance strength is what our real observable is that we want to measure, and that is then directly related to the big target yield. That's indeed here, and then you have the mass of beam and target, your stopping power, and your wavelength. And then you can calculate that if you make the measurement happen. Okay, so how exactly does that work with Dragon? Okay, so Dragon, our detector of recoils and gammas of nuclear reactions. So that's basically what this looks like. So it's a 20-meter long electromagnetic separator. And let's start at the beginning. So first, we have to create the reaction at the target. So that's kind of hidden here under a detector array, but there's a zoom in of the gas target shown over here. So it's a differentially pumped recirculating gas target where we have hydrogen or helium gas, depending on the type of reaction that we're studying. So if you have alpha capture or proton capture reactions that you're looking after. And then you essentially have the, as we were showing earlier, you have your, for example, proton capture, you have your compound nucleus that you're building, and then de-excites, which is your first signature, which you can detect in your close-packed gamma ray detector array. In our case, mostly using BGO detectors for high efficiency. It's also position sensitive, so it's second. So that's step one. But then, of course, the main part is here now we have to get rid of all the beam particles that are making it through, right? So because most of the time, nothing really happens. You shoot the beam through. So the majority of particles downstream of your target goes to the beam. So, and they also exit the target in a range of charge states. So you have to do a charge state selection. That's the kind of what you do with your magnetic dipole. So you have charge selection here, and then mass selection in your electrostatic deflectors. And then you have this kind of stage of separation ×2 to increase your suppression factors. And you can get up to 10 to the 15 or 10 to the 17 for alpha capture reactions. Now, once you're all the way here, and hopefully mostly suppressed, then you have your end detector station where we have either a silicon strip detector or an ionization chamber or a mixture of both. And we also have a set of MCP-based timing detectors where you're shooting your beam through 2 carbon foils. Then you create secondary electrons, which are then deflected to via electrostatic mirrors into the microchannel plates. So you get a start and a stop signal. So you measure the time of flight there. Plus you measure the time of flight from gamma detection to recoil detection. That's your other signature. So you can make coincidence measurements between the recoil detection, so a heavy ion detection, and a gamma. And from that, you get your big target yield, from which you can extract your resonance strength, and you feed that into the thermonuclear reaction rate, which depends linearly on the resonance strength. And in the exponent also depends on the resonance energy, where we also have ways of measuring that. Okay. There we go.
Click on the screen. It's because you closed the Zoom.
Okay.
And
There we go. Okay, so again, here just the beam path coming in, going through your first magnetic dipole, then you have quadrupoles for focusing, going through your ED, and then you do that ×2. Along the way, we have various types of diagnostics. I'll talk about this in more detail for one particular experiment later, so I'll leave that for the moment. And here it's just basically schematic of the detector station where you have your 2 microchannel plates sitting here, followed by your ionization chamber or detector. With that, this is a very typical example on how we can then separate beam from recoils and make integrate over the number of particles. Okay. So, and this is kind of what the whole thing looks like at TRIUMF. This is our isotonic ball. We have the big electrostatic dipoles with the 20-meter long separator. Here's a close-up of the gas target with the BGO detectors around that. And then we can also just remove the entire gas target and put in a different type of target, an extended target, which is what we call sonic, which has, like, because it looks like a hedgehog, but also because it has silicon detectors that are silicon telescopes around there. So you can perform elastic scattering alpha PP reaction measurements as well. And for those who are curious on what it looks like in these electrostatic dipoles, that's just a picture of, actually a picture of Emma, which is a sister experiment, but they look more shiny and new. And it's also not trivial to just open up the big tanks with it's quite unique the crane and a lot of preparation to do that. But yeah, so essentially that shows you the beam pass. So only particles that have the right trajectory can pass a certain voltage, and then you have high voltages up to like 200 kilovolts for the first electrodipole, and a little lower for the second one. So with this, Dragon essentially been able to measure a whole range of radioactive capture reactions involving radioactive species. So that's kind of a list of it, and it's still the oldest device of its kind. So it still holds the record of radio capture measurements with radioactive beams. And most of the type of measurements have concentrated in this area. We're kind of limited otherwise in terms of rigidity. And that includes importance for environments like novae, type 1 extra bursts, and Crocodile supernova, for instance. So, and of course,
When you say you have the world leading measurement, you mean the smallest uncertainty of the cross section?
the only one, essentially.
Only one.
Yeah. Yeah, the only direct one, yeah. I should say that, direct. So it's always indirect ways to target these. So, of course, now want to dive into some examples on what we have been able to do with Dragon in the past. Starting with beryllium-7 alpha gamma as one of the highlight experiments. So why do we care about it in the first place? Well, maybe we should track back. So it's important breakout reactions from our PP chains to the CNO cycles for once. And it kind of affects the conditions, meaning the proton to seed ratio in the early neutrino P process in Crocodile supernova. Because it's, if you look at this reaction flow over here, you have the triple alpha process as a function of temperature, and you have the beryllium-7 alpha gamma rate as a function of temperature. And this is kind of the temperature window where it becomes important for the MOP process. And you can see that it's competing with the triple alpha. The problem is here, if the triple alpha process is the dominating one, then you're producing a lot more seed nuclei, which later on act as proton poisons, so it absorbs proton absorber and leaves less free protons that can then capture antineutrinos and produce neutrons in these Crocodile supernova environments. Whereas it will be reduced if beryllium-7 alpha gamma is the dominating reaction. And by influencing these conditions, it has an effect or could help to explain the abundance of certain P nuclei, so these 35 neutron deficient stable isotopes above mass 74. And that's kind of why we started investigating this one, because there were still large uncertainties on this type of reaction ratings relevant energy and temperature regime. Now, what was the status at the time of the experiment? So there were still various unmeasured resonance states up there in carbon-11. And with that, of course, you have a huge uncertainty on your reaction rate. And Dragon was able to perform the first measurement. So why is this challenging? First of all, they're very weak resonances. So you have very low number of recoils appearing. Second, you have an issue with the Dragon acceptance. Of course, looking at this as an experimentalist, we first thought, oh, it's way out of our acceptance range. It's a factor of 2, larger than what we usually do. So can't do it. And well, we can do it, turns out, but of course we have to think about it a little bit harder. First of all, let's have a look at what the conditions are for Dragon's acceptance. So for each reaction, you kind of have to look at the kinematics, and it's very much depending on the p-value of your reaction. whether what your acceptance will look like at a certain energy. So what you see over here is essentially your maximum recoil cone angle as a function of the center of mass energy. And you can see the dependence here. So for something like beryllium-7 P gamma with small q value, you have continuous rise of your recoil cone angle because the minimum is already at the center of mass energy equaling the q values somewhere down here. Whereas with other reactions with a large q value, you have a decrease in the cone. So really depends on which reaction you're studying. You have to look into what the conditions would be. Of course, that only is the case if your entire center of mass energy is essentially converted by the emission of a single gamma ray. In reality, what you have is usually a cascade of decays. So it's not just a direct transition to the ground state. So you have like each decay happens into some direction in the center of mass system. So what you end up with is a polar angle for your recoil, which is below the maximum calculated based on this. So that's why your whole distribution would be shifted, and this is just showing a gamma cascade decay and simulated versus if you were to use a direct transition to the ground state. And of course, you're folding in target straggling as well. Okay, so how to get around this? The idea is now that we have to benchmark our transmission through the separator with simulations, which we had to do before as well. So we had a Gian simulation for the acceptance for simulating the transmission through the separator from the target all the way to the undetected station. And we had to benchmark that, of course, with something that was known, which in this case was a strong resonance in lithium-6 alpha gamma, which also had a similarly large cone angle as the barium-7 alpha gamma reaction in the energy range that we were looking at. And what you can see here is our separator applied signal, so the time from detection of gamma ray till the detection of a heavy recoil, which is like our nice clean signal in this case, not much background. And from that, we determined the resonance strength, which was in beautiful agreement with literature. And from basically this measurement was then used to benchmark our GN3 simulations, which then allowed us to also go ahead and make a measurement for beryllium-7 alpha gamma. So what do our particle D spectra look like in this case? So what we have here, depending on which configuration we have in the end detector, but you essentially have your energy deposit in the DSD once the time of flight between, which we can reconstruct between the microgel plate and the detection of DSD. So you can't really do that nicely with the ionization chamber because you have much worse timing resolution. But you can see now here these beautiful clean particle D spectra, clean background for the various resonances. One resonance was measured as a reference, which was known in the past. And from that, you can then defer the contributions of the individual resonances to the entire reaction rate, which is shown here. You actually see that like the 110, which was one of the unmeasured one, was actually only a very minor contribution to the reaction. But nevertheless, it will reduce your uncertainties if you make the measurement finally. And just for completion, again here, we can see what we call a BGO position, Z position plot, where you essentially have the number of counts as a function of target position. So you can make sure that you're centering your resonance in the target, right? So if you're coming in at too high or too low beam energy, your resonance will not be at the target center, and you might be missing some of the strength that you're making a measurement. But you can always, using this plot, you can always verify whether that's the case if you have a statistic. And that's then overlaid with a simulation, which also again matches very nicely. So what we found out, again, these are usually the final nice plots for the reaction rates comparing them to previous compilations. And what is visible now is that our present work here in like this pinkish color has reduced the uncertainty on the reaction rates by up to over 10% in some of the regions, some of the temperature regions. That means it's now sufficiently constrained for nucleosynthesis calculations. And also this measurement, of course, proved that we can now also target other type of reactions that have large coordinates. Now, the change in the radium-7 alpha gamma range here has only a minor effect, but we now have to look into calculations together with other important reactions in the repeat process. There's, for example, the fluorine-10 alpha P reaction, and then essentially this means a whole new compilation work to really explore what the effects are. All right, so that was one challenging part. Gets more challenging though. There's nothing ever comes for free. So in the past, the direct measurements have focused on capture reactions that involve the ground state of particular species, but has been ignored for a long time because it was thought too difficult what the actual role of isomers is. Because if you have an isomeric state in a certain environment, they can basically act as entirely separate nuclei. So they can influence the nucleosynthesis pathways as well and create maybe new pathways. So really it needs to be entered as a separate reaction as its own species into these reaction networks. And there's, I think, most physical environments actually have reason to believe that isomers play a significant role. But of course, the data, access to data is a problem. The other thing is alpha N reactions, which we also have ignored for a bit here, which can play a very essential role in the evolution of the chemical elements. But of course, detecting the neutrons as your coincidence signature is also a challenge. So we can do this in reverse kinematics, but need to, of course, find a way to measure the neutrons in coincidence with recalls. So let's start with the issue on the isomers. So the very famous example of where this plays a role. Anyone familiar with this? Nope. Good. Great. Okay. So anyway, so let's start with something that is kind of a famous case for where an isomeric state is involved. So first of all, this involves the cosmic gamma ray emitter, aluminium-26. And it's important because it's a radioisotope. So we can really look into the processes that are happening in stars in our Milky Way. And the reason for it being a star tracer is that it has a relatively short half-life on a cosmological scale, but it's long enough lived that it's not completely uncorrelated from where it was produced. So it provides a snapshot of the galaxy, of nucleosynthesis in the galaxy at a certain time. So it's really evidence for active nucleosynthesis observing this gamma ray signature, which is here as an example from the COMTEL telescope. From the COMTEL image. So that's shown here, and it was known that this kind of coincides with clusters of massive stars. So this is evidence that aluminium-26 is produced in massive stars, and is also a trace of star formation. But it also, in a sense, provides information about the early solar system by so-called extinct aluminium-26, aka its daughter isotope, in which it decays into, by studying pre-solar grains or asteroid axes of meteorites. So you can kind of combine these things to paint a picture of the evolution of our solar system and galaxy. And that means if we can really pin down the origin of these isotopes, it tells us about the circumstances and conditions of the early solar system. And fun fact, it was actually already predicted in the 50s that aluminium-26 must have been somewhere present in the early solar system to provide a heating source to then melt the icy planetesimals in the early solar system and thereby influencing the conditions for life later on. So it's very fundamental. And of course, it would put constraints on the chemical evolution. So, however, as always, it's a nice story, but there's always a debate happening in the background. And this regards the actual sources, not just massive stars. It might also be happening in HB stars or nova ejecta. again, various signatures tell a different story. It doesn't mean that they exclude each other. But at the moment, there's still an overestimate from the many present from the Stellar models for the actual amount of aluminum 26 available. So you really need to constrain the reaction rates to reduce at least that uncertainty that you have some control over. So all of these astronomical observations are available, but now you have to understand them by putting in the nuclear physics input and reducing the uncertainties. Okay, so again, I promised an isomeric state. So aluminum 26 isomeric one photon capture of that is a way to destroy aluminum 26. So we need to understand the production and destruction mechanisms of it. And as I was saying, most of the experiments have focused on the ground state in the past, but the nuclear synthesis here is complicated by this 0+ isomeric state, which lives for 6.3 seconds. And if you see that, of course, it's a 0+ to 0+ state, so the super low decay 100% going into the magnesium 26 ground state. That means it doesn't populate the ground state of the aluminum 26. That means it also bypasses the emission of the gamma line, the characteristic 1.8 gamma line. So that means that any information about elemental abundance that's inferred from the gamma ray emission doesn't include any of the isomer. Now, that means this isomer will ultimately influence our observational signatures. And a way to reduce this uncertainty is, of course, understanding the capture rate on the isomer as well. And there's supposed to be, although like a resonance at 447 kV in the center of mass system, which was of interest for us. And that's exactly what we were trying to target with DRAGON. Okay, so again, you start with, can we even produce that beam at TRIUMF? That's your first big question, otherwise we don't have an experiment. And it was possible to do so, but it doesn't come out as just here, it's your isomeric beam, but it will always come with a ground state. And you have to find a way to separate that. So that's essentially, we also have some sodium combination, which didn't really harm us. So that's step one. So we're able to get a decent amount of beam current that is required to make our measurements to get high enough statistics. And we are measuring the 447 kV resonance in the isomeric system, as well as a reference resonance at 369 in the ground state system to make sure that our methodology was working out. And they also have to then take charge distribution measurements with a beam of aluminum and silicon to account for your charge state fraction. Okay, so one important part here is that you have to find a way to normalize, meaning we're usually taking Faraday curve readings regularly upstream, downstream of the target every hour, so you can measure your beam currents and normalize that. However, of course, you would have ground state as well as isomer in that beam, so you can't use your normal method to do that. However, since we know that the isomer decays into the via beta decay, we can measure essentially that signature. And we do that by when you come in with your beam, we have various diagnostics boxes where we also have SID systems installed to suppress any of the unreactive beam. And when you're tuning with beam, and then after that, because otherwise you don't have enough current on your Faraday cups to diagnostics, then you will essentially adjust your voltages. So you're scaling to what the voltages should be like for transmitting only the recoils. And if you do that, the beam is moved to the left side if you look down beam direction. And that means we can suppress it on one of these sets. So that's where the beams sit throughout the experiment while you're taking data. And there it also decays. And then you essentially have the emitted positrons that are then moving up this horn, as we call it, where you have around it at 180 degrees two sodium iodine detectors, and then you can just measure the photons from the 511s from the annihilation, and that's your signature and your count for how many isomeric, how much of the beam was in the isomeric contribution. Okay, so yeah, that's just a different view to make it a bit more easy. Again, beam goes through, slit, stays here, deposited, and you have the annihilation signal in your sodium iodines, and then you integrate that, and that gives you your number of recoils, beam particles, sorry.
You just lost the share.
I saw that, it just, Zoom just crashed. I can reopen it, I suppose.
This video catches, so
Okay.
I would say don't.
Just continue.
Just-
Good. Okay, sounds good. Okay, so now these are particle ID spectra for this particular measurement. So what you see is your separated time of flight, again from target to end detector, versus your local time of flight between the entities. A very nice cluster of events background free, which is your reference measurement in the ground state. And then same thing here, the total energy deposited in the ionization chamber as a function of MCP time of flight, and you can see how nicely they're separated from your unreacted beam. So it's great. And then we go to the very low, much lower statistics measurement for the resonance of interest in the isomeric system. Again, nicely background free, 10 golden recoils as we usually call them. And then the analog plots down here. And again, they show up in the same area as they would for the other resonance. So again, nicely separated from unreacted beam. And from that, we can then calculate a resonance strength, which is exactly what we did. And again, just to summarize, good agreement on the ground state part. We also moved off resonance, so we actually played around with beam energy that you deliberately placing the resonance outside of the target to make sure that you don't have direct capture contribution that might make up these 10 counts. So you want to be sure that nothing is seen during those measurements, which was the case. And then we extracted the resonance strength for the 447, and it turns out that was actually relatively high, so 432 milli-electron volts. So high for the system. So there's much higher strength available on the electron volt level. But yeah, so that's what we got. And this was a nice confirmation of an indirect study that used a transfer reaction on silicon-26 as essentially a surrogate reaction to populate the same types of levels. And they also had like predicted a strength of the order of a few hundred milli-electron volts. So this is actually a very, very nice agreement. And then you can, again, calculate your contribution of each individual resonance in the system to the thermonuclear reaction rate and compare that to previous combinations that were not including any direct measurements or information about direct measurements here. So what we actually found is that I was saying earlier, oh, you can't use the ground state rate, but in this particular case, they're actually not too far off. So they were treated as individual species, but they were using the same rate based on the ground state measurements. And we're actually not too far off from that, now having measured the one significant resonance in this reaction. But of course, there's a whole range of other resonances that might still come into play. None of these have been measured directly. So they might be of importance at higher temperatures. And that's something we can target in the future. So, bit of an outlook. Of course, that's not the only science case involving an isomeric state. There's more. So we have, for instance, the chlorine-34 metastable state, which is of importance in oxygen neon nova environments. And because it influences the abundance of sulfur 34, and now you ask yourself, okay, why do I care about sulfur 34? Well, because it's potentially a marker for this ratio might be a marker for where presolar grains are of nova or coccolith supernova origin. And by reducing the uncertainties on the reactions, we can then really see where these grains came from. So we're actually not doing this with Dragon, but I'll talk about it in a moment. So, of course, there was no experimental data available on this one either. So you are essentially looking at previous rate populations, assigning variations in the abundance up to a factor of 100, depending on the reaction rate variations. And of course, we want to narrow that down significantly. Again, something the isomeric state reaction rate has been treated just by using ground state, just as one rate, but of course they could act as entirely different species. And there was no direct data available in the relevant energy range. And that's something you want to change by taking a direct measurement of, so this is actually, simultaneous measurement of the ground state, as well, of the isomeric state, dP and dN reactions. So this is kind of an indirect way of determining the reaction rate for radiative capture reaction, and that was done, or is planned to be done in the future, and one of the other facilities at ISAC at the higher energies. So you do that with MR plus Tigris. MR is electromagnetic mass analyzer. It's a sister experiment, which kind of uses this symmetric configuration of electric dipole and magnetic dipole to focus energy and disperse in mass in the focal plane. So it's a true spectrometer rather than just a separator. And then you have your signature, the gamma detector array around your target. So you have your gamma signature detected over there. And then you have a silicon array close to the target where you can also, at backwards angle, detect the protons as your signature. Okay, so that's something that's on the books. And the proof of principle was already done that this works. The simultaneous measurements of dP and dN. And now finally, I know I'm probably out of time, but I will quickly touch on alpha N reactions that I was mentioning earlier. They're equally interesting and should be studied. So in sometimes you also have the alpha N reaction channel open. So you want to find a way to measure these cross sections as well. They might be important for some environments where our processes are happening. We already know that our process happens in our neutron star mergers, but there's some observational evidence that there must have been our process happening much earlier in the universe, because there are some nuclei that must have been produced via the arc process in older stars or also in satellite galaxies. So it's not quite clear what the origin of those is. And one potential site called supernovae, where you have just after the collapse, you have your scenario of the alpha process or weak arc process, where you have a series of alpha N reactions which drive up the reaction rates to heavier elements. So it's very important to measure these. And if you look, we always, as mathematicians, always look at sensitivity studies and understanding, okay, which reaction rates are now important to measure. And of course, in this case, means we need the radiative ion beam facilities, radiative beam facilities to help us doing these in inverse kinematics. Okay, and we can do that at Dragon by, again, having a different detector configuration. So we can place an array of neutron detectors just downstream of a gas target, in addition to the other detectors, the VGO that we have around there. These are so-called organic glass scintillator detectors for neutron detection. They're relatively bright, so high efficient. You can shape them in, I think, almost any form. They're solid, so much easier to handle than liquid scintillators. And in this case, you have to, of course, look at the reaction kinematics as to where you place the detectors, where you expect the neutrons to be emitted. And then you can do a pulse shape discrimination to distinguish between your alpha and, between your gamma and alpha gamma and alpha N reactions. And that was done very nicely here with the proof of principle measurement that we did on neon 22 alpha N or alpha gamma. So, which alone is already in reaction for the S process. However, also a nice proof of principle measurement because it has a strong resonance. The one for MEV that we could use for our purposes. And here's a picture of when this actually happened. We spent this hot cross to assumption of the target with the neutron detectors, 8 of them in total. And then we're able to, this is our singles measurement with an MCP term of light and the ionization chamber energy loss. And then you can do coincidence measurements between time of flights. And of course, oops, where's that picture? I think there's a slide missing. Oh, 1 second, sorry about that. Yeah, that one, that's the one I want. Okay, so, and here's your actual signature. You can differentiate between your neutrons and your gammas, and you can place that as well on your recall plots, and then you can unambiguously identify the events correlated with the alpha N reaction. So that's actually the first time this was done in a recall separator. So that's why it was a big deal for us to do this. And our resonance strength so far is in good agreement with literature. There's a lot more to figure out on the simulation side until then. But then once that's done, we're going to go explore a more weak resonance in the same reaction before we then turn our attention to other interesting science cases for alpha N reactions that we, for example, outlined in the sensitivity step. So Dragon really has now a lot of capabilities. We have the neutron detector array, we have a normal VGO detector array. We can replace the VGOs with lanthanum bromide or cerium bromide detectors for better timing resolution. We can remove the target and install sonic, or we also can now put high purity germanium detectors around it. So if you need the high energy resolution rather than high efficiencies to measure the gammas. So a lot of new things that we're now able to do. And with that, I think I gave you like a big enough overview of all the things that can be done. But yeah, so in summary, as we really want to understand the nature of and the role of the nuclear reactions underlying in these nuclear synthesis processes, radiative capture reactions are the key to understanding these reaction pathways. We've done the first ever study of proton capture in an excited state, which was the aluminum 26 case. There's within reach more information about radiative capture reactions on isomeric states with the Emma and Tigris facilities. We've also done the first image kinematic measurement of alpha N reactions in the recall separator. And as you were just seeing with all the other new detector arrays, there's a lot more to come for us in the future. Okay, then I would like to thank, of course, all the collaborators involved. And thanks for listening, bearing with me.
Good question. One question? Well, while you are thinking about it, I can ask one question. So it's, I assume that we are measuring with the X-ray from the alpha particle object directly, and then that's a nuclear synthesis how we were observed up to now, I assume, like COMTEST 26 are aluminum is from X-ray measurements, right? And so have you seen any like outlandish like discrepancy between what is currently modeled in nuclear synthesis versus your direct measurement? Do you have any examples? Just one?
Yeah, I mean, that's honestly, that's a lot of examples. I mean, the one with the sulfur by itself is an issue. So in that case, your observable is your pre-solar ray analysis, and your ion microbe probe analysis gets better and better. So we need to be more and more precise in the nuclear reactions. that, or to reduce the nuclear reaction uncertainties. So that's one example what it is, but in most cases, there's hardly, in most cases with radioactive species, you still have some discrepancy between the observations and your nuclear physics input in this case. But that's where the computational science comes into play. You get more and more complete reaction networks, and you have to, of course, also include the actual dynamics in the stars, so they produce rotation, for instance. So that it gets a lot more complicated. It's not just the nuclear physics part, but there's a lot of factors that eventually play a role. So we can only do the whole big scheme. You can only do very small parts at once. So the big picture is still a lot of things are not quite correlated.
Right.
Yeah. And again, the aluminium itself is the example, right? We are
Right.
producing the abundance.
Any other questions? Sure.
Yeah, just maybe to push into that line of questioning a little bit more. So like for the R process story, it's been, great to get clarity on that interaction network processes. And I think that's somewhat clarified why, a lot of the biggest stars, and you can't really get it.
Yeah.
Between the winds, are there specific stellar processes we should think about that, are at play here that people are arguing over that would give you more or less 26? They're more just, they have all this other furnace.
So, okay, so for the 26, we know what kind of processes can happen to some level at what temperatures they would happen in various different types of stellar scenarios. But I don't think at the moment that we need any other input on that. Yeah, I don't know. You're asking if
I guess I'm asking so it seems like we're pretty sure we know where it is, but is it a question like temperature profiles?
Yeah, of course. Yeah, that's of course temperature profile. Yes, absolutely. So all of these conditions in the stars, if we get more data on that, then we can of course compare that more directly with our nuclear physics measurements, and especially temperature is very important when you're debating the role of the isomers, because that kind of depends on when are they in equilibrium and at what point does the isomer contribute more than the ground state and vice versa. And so all of these considerations have to come into play. Yes.
As you're doing more and more experiments, can you make predictions for the experiment you're about to do based on past ones? And would you do that by physics, or would you try something, sort of black box like a neural net? Is there some way to learn or make predictions based on past experiments?
You mean predictions about a reaction rate?
Reaction rates based on similar. You put in all this data and you either model it.
I mean, you still have to put in every reaction by itself, right? Of course, in some cases there's a lot of assumptions made when you feed that into your calculations until you have an actual measurement, and that kind of again makes predictions of, oh, this reaction is important in this environment or in this environment. But of course, sometimes you also have to go back and correct yourself once you actually change your input parameters to something more realistic. So the impact of a certain reaction in this environment may change again. So in that sense, sure, you can make a prediction, but you have to test it. So, and a lot of times you have to actually correct it. Yeah.
If there's no other question, I have a last question. I'm sorry, this one I feel like I should ask. If you don't mind, you showed your showcase before you jumping into value. There's a lithium alpha capture, and you were saying that it's matching with literature. And then when I looked at it, your statistical uncertainty was very, very small, but your systematic uncertainty was very large.
Yeah.
So can I ask what is original system?
Yeah, systematic uncertainties. So, as I was saying earlier, especially for that experiment, we're relying on the simulations for the transmission efficiency through the set rate. That simulation depends very much again on the input parameters for branching ratios that you feed in. And you have to then take that into account, and you end up with about a 10% plus under uncertainty for your GM3 simulation. So that's kind of the dominating uncertainty for us on the systematic side. So yeah, that's the simulation part that feeds into this. Everything else is much below that, more of the order of 2.5 to 3%. So yeah, if we could reduce that, that would be helpful.
All right. Any other questions? All right, then let's thank you. And again, tomorrow's different topics, so
Yeah, very different. Yeah.
thank you all for coming. And I have a class, and so,
Oh, you have a class. Okay.
yeah, so I need to but this yeah, so Joe's going.
Yeah.
So
Pretty cool. But I did using the T. But I'm happy you can talk. Or not.
Oh, start in the schedule. You can just start.
just because I couldn't find any other ones, right? Right, maybe because I don't know why. Thank you. So I hope that the schedule, meeting schedule and everything is clear for you.
Yeah, I guess there's no more meetings this
Yeah.
afternoon. Maybe there is. Yeah, maybe there. So, okay.
Okay.
Multi-factor. Yeah, that's quite possible. So